Good morning and good afternoon. Thought we could go through some answers here to review problems out of your homework packet, starting with number 66. It says, how are all the variables of pressure, temperature, volume, and moles related to each other? So pressure and volume are inversely related. Volume and temperature are directly related. Pressure and temperature are directly related. And volume and moles are directly related. So of these four variables, the only inverse relationship would be pressure and volume. Next problem is number 68. If you have any two gases in different containers that are the same size, so volume, temperature, and pressure, what can you deduce about the number of moles of gas in each balloon? Well, if you have the same volume, temperature, and pressure, according to PV equals nRT, since R is the same, P is the same, V is the same, and pressure is the same, the moles must also be the same. Alright, next problem, number 69. If two balloons of equal volume, pressure, and temperature, one is filled with ammonia, which is NH3, the other is filled with hydrogen, which is H2. What can you conclude about the kinetic energy of the molecules in each balloon? Well, since they're at the same temperature, they have the same amount of kinetic energy. What can you conclude about the speed of the molecules in each balloon? Well, they have the same kinetic energy. However, H2 is much lighter than NH3, so the H2 molecules must be moving faster. Part C, how is it possible for these balloons to have the same pressure? So how could these balloons have the same pressure? Well, the H2 molecules, or particles, hit the container walls more often, since they're moving faster, but since they're lighter, those collisions are weaker. NH3 particles hit fewer times, but with more force since they are heavier. So these two cancel out. H2 particles hit more often, but the NH3 particles hit harder. Next is number 71. We've got a 5-liter flask containing 0.6 grams of oxygen at 22 degrees Celsius. What's the pressure inside the flask? This is a PV equals nRT problem. We're looking for pressure. The volume of the container is 5 liters. We exchange 0.6 grams into moles by dividing by the molar mass of O2. So that's 0.01875. R is 0.08206. And our temperature in Kelvin is 295. Solve for pressure, we get 0.091. Next up is number 72. We need to make sure we balance it up. And this is a gas stoichiometry problem, so starting with 25 grams of NO2. Change this to moles. Molar mass is 46.01 grams of NO2 for every mole of NO2. And we go to our mole ratio. There's 1 mole of N2O4 for every 2 moles of NO2. And this gives you 0.272 moles of N2O4. Now we can do PV equals nRT. Change 770 millimeters mercury in the atmosphere with 1.01 atmospheres. Moles is 272. R is 0.8206. Temperature We're going to add 40 degrees to 273, 313. Solve for your volume of 6.9 liters per N2O4. Next up is 73. A mixture of 4 grams of hydrogen and 4 grams of helium exerts a pressure of 0.48. What's the partial pressure of each gas? Well, we need to change them to moles. So 4 grams of hydrogen is 2 moles, approximately. And 4 grams of helium is approximately 1 mole. So the total moles of helium is 1 mole out of a total of 3 moles. So we multiply that fraction by the pressure, the total pressure, we get the partial pressure of helium. That partial pressure is 0.16 atms for helium. And if you do the ratio for hydrogen times your total pressure, you get 0.32 atms per. Next up is 74. Consider separate 1 liter samples of hydrogen, xenon, chlorine, and oxygen all at standard temperature and pressure. Rank the gases in order of increasing average kinetic energy. Well, since they all have the same temperature, they all have the same kinetic energy. Next question, rank the gases in order of increasing velocity. Well, the faster molecules are going to be the lighter ones. So hydrogen is going to be the fastest, xenon being the heaviest is going to be the slowest, followed by chlorine that has a molar mass of 70, oxygen that has a molar mass of 32, and hydrogen that has a molar mass of about 2. How can the samples of hydrogen and oxygen have the same average velocity of molecules? What would you need to do? Well, there's a couple options. You could cool the H2, that would make them move slower, or you could heat the O2, that would make them move. Next is 75. It says a 1.58 sample of C2H3X3 gas has a volume of such and such, a pressure, and a temperature. We want to know element X. And this gives you the hint to find the molar mass of the element. This is going to be a 2V equals nRT kind of problem. We know the pressure, since you can change 769 millimeters mercury into atmospheres. It's 0.999 pressure. Volume is 0.297 liters. And we don't know. And temperature is 308. So, solve for your moles, you get 0.0117 moles. Now, if our sample has a mass of 1.58, if we do a mass over the moles, we get the molar mass. We divide these, you get 134.6 grams per mole. And I'm going to subtract the mass of 2 carbons and 3 hydrogens. That'll leave us with 107.6 grams per mole. And that's for X3. We got rid of the C2 and the H3. So to find the individual mass of X, just divide this number by 3. And you get 35 and some change grams per mole. So what element is this? It's closest to chlorine. Number 76. You've got a synthetic atmosphere that's 2 moles carbon dioxide, 20 moles oxygen, 78 moles of N2, and the total pressure is 0.987. Calculate the partial pressure of each gas, and then what is the total volume of the atmosphere. So we're going to take our fraction that is carbon dioxide, so 2 moles of CO2 out of a total of 100 moles of gas, times the total pressure of 987. That would give us the partial pressure of carbon dioxide to be 0.01974 atm CO2. Do the same ratio for oxygen, 20 out of 100. Gives you 0.1974. And then you can just subtract from 0.987 to get the partial pressure of the N2, 0.77. The second question asks if the temperature is 30 degrees, what's the volume? This is just PV equals nRT. We use the total number of moles, 100. Solve for your volume using the total pressure. Let's skip ahead. You get a volume of 2519 liters. '77, you're holding 4 balloons, each containing 20 grams of different gas. The balloon containing which gas is the largest? So if you have 20 grams of each gas, you'll have the most particles of gas that has the lowest molar mass. Since helium has the lowest molar mass, you're going to have the most moles and therefore the most particles. And you have the most particles, you're going to have the most collisions, and so you're going to have the biggest balloon. 78, you're playing with a balloon on a warm day in Geneva. Suddenly the Celsius temperature doubles. Which of the following is true? So let's say a warm day. A warm day is 30 degrees Celsius. And then all of a sudden it doubles to 60 degrees Celsius. Well, what you have to keep in mind is that Celsius is not our go-to temperature for gas laws. This would be 303 Kelvin. And this would be 333 Kelvin. This is clearly not a doubling of the Kelvin temperature. So the volume is not going to double. Pressure is not going to double. The volume is not going to get smaller, and particles are going to move faster, but that'll just cause the volume to increase a little bit. Which of the following changes to a sample of gas would increase the average kinetic energy of the gas? Well, if you want to change the average kinetic energy, you just have to change the temperature. None of the other factors affect kinetic energy. Number 80, you've got a container with 3.4 grams of nitrogen and an unknown mass of carbon dioxide, but we know the partial pressure of carbon dioxide is double the nitrogen. How much carbon dioxide is in the container? So 3.4 grams of nitrogen is 0.121 moles of nitrogen, and just divided by the molar mass. And if we know the carbon dioxide's pressure is double, that means it must have double the number of moles. So if we do this times 2, you get 0.242 moles of CO2 floating around. And this just wants to have a mass, so multiply this times the molar mass of CO2, and you get 5.33